Today we will see Prim's algorithm. How Prim's algorithm is used to find minimum spanning tree. We know what is minimum spanning tree. Uh, Graph is given with weight. The problem is to find the uh, spanning tree with minimum weight. Spanning tree is the tree which includes all the vertices of the given graph with no cycle. The spanning tree with minimum weight is called minimum spanning tree. So we are using Prim's algorithm to solve minimum spanning tree. What is minimum spanning tree? It's a weighted connected acyclic graph that contains all the vertices of the given graph. Minimum spanning tree means the spanning tree with minimum weight. That is sum of weight of all the edges should be minimum. That is called minimum spanning tree. So Prim's algorithm is very popular algorithm that is based on greedy approach to find the minimum spanning tree for a connected, weighted, and undirected graph. Here the Prim's algorithm uh, add, adds edges step by step to find the minimum spanning tree by applying greedy approach. First, we will see algorithm for Prim's greedy approach. Start with an arbitrary vertex and add it to the minimum spanning tree. Initially, the spanning tree has no edge and the total weight is 0. Now, take the edges one by one from the given graph and add it in the minimum spanning tree. And if there are more than one edges for the particular node, choose the best outgoing edge with minimum weight. That is the concept of choosing the edges. Then add the edges in the spanning tree. Repeat this process until all the vertices added to the graph and there should not be any cycle. And all nodes should be visited only once. The second step is repeat the following process until all vertices are included in the minimum spanning tree. Here it contains two subsets. Select the edge with the minimum weight that connects a vertex in the minimum spanning tree to a vertex outside the spanning tree. So choose the initial vertex as a visited vertex. For example, A. So from A, find out the outgoing edges. So choose the outgoing edge with minimum weight. So that is called greedy approach. For each and every step, we are choosing the edge with minimum weight. So choose the edge and add it in the minimum spanning tree. Then again, there are two nodes in the spanning tree. Again, find out the outgoing edges for the two nodes. Then find the minimum weight edge. This process is repeated until all the vertices added. When we add or choose the edge, they should not form any loop. And this is Prim's algorithm. Input is the algorithm name is Prim's to um, find minimum spanning tree. The input is graph, it's a connected weighted graph. The algorithm constructs minimum spanning tree. G is equal to V comma E. Graph is a collection of vertices and edges. Each edge is assigned with weight. The output is ET, that is edges in the minimum spanning tree. It's an edge with minimum weight. It's called minimum spanning tree. Initially, VT is the vertex in the spanning tree. So we are taking any one node as an initial vertex. And initially the edges are empty in the minimum spanning tree. So the loop is repeated for all the vertices. Modulo V is number of vertices minus 1 because already we have selected one vertex in the minimum spanning tree. So this loop is repeated for V minus 1. So find out all the outgoing edges from the visited vertex. So find out the edge with minimum weight. So that vertex is added in the spanning tree and the corresponding edges with weight is updated in the spanning tree edges. So this process is repeated for all the vertices in the given spanning tree. So after finding the spanning tree, return the minimum spanning tree. This is the output of Prim's algorithm. Example, take a graph, find the minimum spanning tree for the undirected, weighted, connected graph. So initially we are taking graph as an input, and the values are written in the table. Initially, the t vertices, we are starting at the vertex A. So A is added in the spanning tree A. So minimum spanning tree, initially there is no edge. So find out the remaining edge. So from the A, what are the outgoing edges? A to B. That is 2B from A is 3. From A, AF is another edge. So 2F from A is 5 and 2E from A is 3. So there are 3 outgoing edges from the node A. And for the remaining vertex, there is no direct path from vertex A. So we are writing 2C from A, no path, this is infinity difference. And from A to D, there is no direct path. So we are putting dash and infinity. Now there are 3 edges in the remaining. A to B 3, A to F 3, A to E 3. So choose the edge with minimum weight. So two edges has the same value. So we can choose any one of them, A to B or A to F. Both will give the same result. In this scenario, we are taking A to B, 3 as a edges in the spanning tree. Now there are two vertex in the spanning tree, A comma B. Now find out all the outgoing edges from both A and B vertices. That is from B to C 1. Then from B to F 4. That is from A to E 6. Now to D, there's no direct path from A to B. So the distance is infinity. Now there are 3 edges possible. So we can choose the best one. It's a greedy approach. The problem is solved in multiple stages. Each and every stage, we are choosing the best solution. It's called local optimal solution. So each and every step, we are choosing the edge with minimum weight. Now B2C is selected with edge 1. Now there are 3 nodes in a spanning tree. Now find out the outgoing edges for these 3 vertices. So 2 F from B is 4, 2E from A is 6, 2D from C is 6. So there are 3 edges. So now choose 2F from B. That is P to F, P to F is 4. Now add it in the spanning tree, and remaining is two edges. That is F2D5, F2E2. Now in this stage, edges with the minimum weight is 2. That is 2E from F. F2E is 2. Choose the edge and add it in the spanning tree. Now we have only one vertices left. Remaining all the vertices are added in the spanning tree. So only one, that is the optimal solution. Choose the edge and add it in the minimum spanning tree. Now this is the final minimum spanning tree for the given graph using Prim's algorithm based on greedy approach. Now we have to find out the total weight of the spanning tree. Add all edge weight, that is sum of weight of all the edges in the spanning tree is minimum spanning tree weight. That is, this for this problem the weight is 15. So this is the overall picture of the spanning tree. Initially the tree vertex A is taken. Initially the spanning tree edges are empty. So we are taking the remaining edges. From the remaining edges, choose the best or the edge with minimum weight. That is optimal in this scenario. So this is called local optimal. Add it in this tree vertices. Again, find out the outgoing edges for visitor vertices. So choose the best one. This process is repeated till all the vertices are added in the spanning tree. So finally check whether all the vertices are added in this tree, and the spanning tree should not contain any loop. This is a high-click graph with the minimum weight. What data structures we can use to implement Prim's algorithm? That decides the time complexity of the algorithm. So the time complexity of algorithm depends on the data structures used to represent the graph and the priority queue. There are two data structures. The Prim's algorithm can be implemented using adjacency matrix and adjacency list. So adjacency array is used to store minimum weight of a vertex to each vertex. And the adjacency list, the priority queue is efficiently used for implementation that select the edges with minimum weight or minimum edge. So priority queue is implemented using min-heap as a data structures. Now we can use either adjacency matrix for implementation or adjacency list for implementation. Now, time complexity. If the adjacency list and the priority queue is used, minimum heap is implemented, and the time complexity is order of V into log E. V is number of vertices in the given graph, E is number of vertices in the graph. And if you use adjacency matrix, the time complexity is order of V square. Adjacency matrix does not depends on the number of edges. It fully depends on the V, number of vertices. Now the both can be combined. Adjacency matrix and array or list. The minimum vertex can be found by scanning all the vertices. The time complexity is order of V square. So there are three different ways for implementing Prim's algorithm for finding minimum spanning tree. Adjacency list and priority queue, adjacency matrix and array. So from this, the first adjacency list using priority queue takes minimum time. The time complexity is less compared to other two methods. So the time complexity of Prim's algorithm we use adjacency list and priority queue is order of V into log E. So space complexity, how much memory it occupies to produce the minimum spanning tree. The space complexity of Prim's algorithm using adjacency list, array or priority queue is order of E for order of V. E is number of edges plus V is number of vertices. The overall representation of Prim's algorithm is adjacency matrix searching order of V square, binary heap. There is priority queue is implemented using binary heap, and adjacency list is order of E into log V, and the Fibonacci heap and adjacency list this order of E plus log V. So this is the time complexity of Prim's algorithm depends on the data structures we used for implementing algorithms. So what is the advantage of Prim's algorithm? Its complexity, which is better than Kruskal's algorithm, which is helpful when dealing with dense graphs have lots of edges. If the given graph contains lots of edges, Prim's algorithm is suitable that takes minimum time compared to remaining algorithms.